Next, we're going to take a look at an example of how to use the rational root theorem to completely factor a polynomial that doesn't factor any other way that we know of. So looking at this cubic function, it's a trinomial, but it is not quadratic, so we cannot factor this with a t-chart. And there's only 3 terms, so we cannot factor by grouping either. So we're going to use our rational root theorem. First, list all possible zeros. Well, this has the same constant as our first example and the same leading coefficient. So our possible zeros are positive negative 1, 2, 3, and 6. The next step is to use synthetic division to try to factor. Remember, if the function factors, it will have a remainder of 0 when you do your synthetic division. If you have a remainder that is not 0, it is not a factor of the function. So to be perfectly honest, this step is kind of guess and check. Now, looking at when we set up our synthetic division, using our coefficients, we've got a lead coefficient of 1. The x squared term has a coefficient of 0 because it's missing the negative 7 and the negative 6. Knowing that at the end, I want to have this spot right here be a positive 6 in order to cancel with that negative 6 and give me a remainder of 0, I probably don't want to try a number that's too big because I'm going to be multiplying by it. I like to start with 1. It's a positive number, easier to work with. So we do our synthetic division, and I end up with a negative 6 here, so when I add them, I get a negative 12. What that means is the binomial x minus 1 is not a factor because I got a remainder that is not 0, or 1 is not a 0 of the function. Well, we guessed, so we're going to guess again. I'm going to, instead of resetting this up, get rid of these values here, and try again with, we got really close. We got a negative 6. We needed it to be a positive 6. So I'm going to try again with negative 1 and see what happens. And we get a remainder of 0. So what that means is x plus 1, don't forget we're putting it back into the asylum, is a factor of the function. And I can use my answer to write the quotient of my division. So we can rewrite our function beginning to factor it in this form. And now I have a trinomial, a quadratic trinomial, which I can finish factoring by the t-chart. So what multiplies to negative 6 and adds to negative 1? Negative 3 times 2 and negative 3 plus 2 will work. So I'm going to finish factoring. Let me label my function here. X minus 3, x plus 2 finishes factoring the polynomial. But the question wasn't write the polynomial in factored form. The question was find all of the zeros. So this is where step 4 comes in, the zero product property. Set each piece equal to 0 after you finish your factoring, and solve for your zeros. So in this case, our zeros are negative 1, positive 3, and negative 2. Now notice, all 3 of those numbers are in the list that we started with. But again, I want to reiterate, not all of the numbers in the list are zeros of the function. One more example, this one we do have a lead coefficient, so I wanted to make sure I showed you at least one example of how to find all of the possible zeros when you've got a lead coefficient that's not 1. So I like to start by listing out the factors of the constant. So what numbers go into 12 evenly? Hopefully you can rattle these off fairly quickly yourself. And then what we do is all of these are possibilities, but we have more possibilities because our lead coefficient is 2. So we're going to take all of these possibilities and now divide them by the factors of 2. Well, the factors of 2 are 1, which won't change any of the numbers we have here, and 2. So we're going to divide all of these by 2 to get our additional possible zeros. Now, if I divide 2 by 2, I'm going to get 1, which is already in my list. So I'm going to move on to 3. Same for 4. If I divide 4 by 2, I will get 2, which is already in my list. If I divide 6 by 2, I'm going to get 3, which is already in my list. If I divide 12 by 2, I'm going to get 6, which is already in my list. So it actually only added 2 additional possible zeros. And of course, when you're using synthetic division, I don't know about you, but I'm not going to want to start with the fractions. So those would be my last resort. If I checked all of the integers and none of them worked, then I would check my fractions. So setting up our synthetic division, using those coefficients. And I like to start with 1 and -1 and just check those out first. So what happened was, can't talk and add at the same time. What happened was when we got down to the end, it was pretty close, but it was twice as big, and it was the opposite sign. So I'm thinking I'm going to try -2 next and see what happens with that. Now it may end up being too big, but that's my thought process when I'm doing my guess and check. Actually, I missed my sign, so that did end up working out perfectly. So, fortunately, we only had to guess and check twice on these 2 examples. You could end up guess and checking for a while. Hopefully, as you were hearing my thought process, that will help you to get yours factored faster as well. So I'm going to set up my remainder and try to factor other than guess and check. So here's our function in partially factored form. And looking at this cubic, it does have 4 terms, but I can't factor by grouping because 2 and 3 don't have a common factor that I could factor out, and neither do 11 and 6. So those would be my coefficients, so I would not be able to factor that further. So unfortunately, I have to do my synthetic division one more time. So I'm going to set that up again. Now with just the coefficients of the quotient that I got once I found that x plus 2 was a factor. Well, we already tried 1. We could try -1 and see what happens this time. This time, it's twice as big. I needed that to be a +6, and I got a +12. So even though I said I was going to use it as a last resort, I'm looking at this and thinking I might need to try that +1/2 and see what happens. So bringing down the 2, multiplying by 1/2, adding them together, multiplying by 1/2, adding. Here I get an odd number. So the fraction didn't actually work because, of course, when I multiply that by 1/2, it's going to give me a fraction, which will not be the 6 that I need in order to cancel. So we're going to try 3 and see what happens. And that's way too big. And I'm thinking the higher the numbers, the bigger they're going to be. So the only one I didn't try was a +2. That was a small number. The other option is to try the 3/2 fraction and see where that gets us. So I'm going to try the +2 first, and then we'll try the 3/2. And fortunately, this one worked. So we can continue factoring our function. So the x minus 2 comes from this factor where I got the remainder of 0. And then I'm going to use the quotient to write my last trinomial. And then this one I can use the AC method. I can already tell that this is going to work. What multiplies to 6 adds to 7, we're going to get a positive 6 and a positive 1. So I'm going to factor this one by grouping. So we get the x plus 3 times the 2x plus 1. So it looks like if I had tried the negative 1/2, that would have given us a 0. And finally, using the zero product property to list all of the zeros of the function, we would get a negative 2, positive 2, negative 3, and a negative 1/2, setting each term equal to 0 and solving. Here's your you try question. Determine all of the zeros of this function. Try listing the possible zeros, and then synthetic division, you're just going to have to guess and check and see what comes up.